Hi, everyone. Can you hear me? Yes, okay, perfect. All right, so you should be able to see my screen as well. Can you see my screen? Okay. All right, so we're gonna get started. So first of all, thanks for joining again. And I'm really excited about this particular chapter. I think here we start to see a couple of the things that are quite important in when training deep learning neural networks. And particularly, we're going to focus on multi-layer perceptrons, which there's very basic neural networks. But here you start to see some of the strengths, and you start to understand why these methods are more powerful than your basic linear neural networks, which we already covered in the previous session. Also, I'll have some announcements towards the end. So we're going to have a new presenter in the next session, which will be great. And I want to encourage people again in the group, if you have, if you're confident that you can do, present one of the chapters and the sessions, please feel free to reach out to me. You can do slides, you can do code, go through the code. Again, we're using the code in the book, so I think that should be relatively easy. You can definitely consult with me, and I'll help you out throughout the process if you really want to get an experience of that. I really want to make it a very flexible and open, program, like I said before, and I want this to be an opportunity for you to, to use the platform to learn and achieve different things. So let's see. I'm just going to check a few things here. Just want to make sure. Okay, so we're live on the YouTube one. That's great. All right, so just going to start the presentation. And again, just remember, you can ask your questions in the chat. I'll look at those questions as I go along. But I have a couple of slides that I want to, actually, it's a bunch of slides, but I thought it was quite important because we're going to start to talk about how to efficiently train deep neural networks. So I think it's important to cover a few of the topics. Unfortunately, I won't be able to go quite in depth as I would want to, since this is an introduction to deep learning. I mean, the book doesn't really give you a lot of coverage on some topics, but the good thing is that they always refer to you to some paper or something like that, which you can always go and try to investigate further. But I will cover the most important ones, which I believe are the most important ones, as I go along. All right, so we are in chapter 4. We're making some progress. I think, let's see, we have 14 chapters. We have covered 4. We're getting there. I think it's going to get really exciting when we move on to the chapters that are coming next. I think so just one thing I want to note here, the deep learning competition, I'll talk about it later. So this chapter was supposed to be today, but I don't think you'd be able to cover all the topics in deep learning competition, which, by the way, are some very, very important topics, because they teach you how to train in GPU, which is quite an important thing in deep learning, but I won't be able to actually cover it. So just going to do a check again. Are you able to hear me well? Because I'm using like a new mic here, but I want to make sure everyone can hear me before I continue. All right, perfect. That sounds great. Thank you. Yeah, like I was saying, I think that chapter 5, what I would do for this one, I will do some recording. I'm actually going to do a couple of recordings on things that I don't think the book covers enough. I think these could be helpful for you as you go along and you're working on your own, your own projects. So topics that identify which are important. So this is the reason why I think I wanted to do it, across a few months rather than just cram everything in 2 months or something like that. This gives us a lot of time to cover a lot of ground. So that's the idea here. Now for chapter 6 and chapter 7, this will be covered by Salim. So Salim is an NVIDIA deep learning instructor. He'll be on the call. He'll cover those sessions. He will share a lot of his experience there as well. He's an instructor similar to me, which I'm really excited about, and actually gives me a break as well. So that's good on both ends there. But I think he will offer quite a unique perspective on his experience with deep learning, and he comes from NVIDIA, so I think that'll be really great to hear from him. And again, as I said, if you really want to help out, deliver some of the sessions that you see that are coming up next, please feel free to reach out to me and we can organize something. I can definitely help you out as well. Let's keep moving. So the agenda for today is quite a long list. That's why I said I couldn't really cover the 2 chapters that I wanted to cover, but hopefully we can, make some progress with multi-layer perceptions, which I think is quite important as we move forward. So that's going to be the main topic. There's going to be some code walkthrough as well, implementation of multi-layer perceptions, some of the components. I think once you understand how to set up multi-layer perceptions using something like PyTorch, you can already start to do and even participate in competitions. So you see, like there's a last section here, which is like a competition on predicting house prices on a data set on Kaggle. So you can already start to use it, which is the exciting part. Now, model selection, underfitting, overfitting, these are quite important topics. I mean, every time you want to train a model, and the first time, don't expect it to get it right. Don't expect to get good results. There's always going to be some issue with your data, maybe. Maybe your labels are not properly data is not properly labeled, or maybe there's some overfitting issue with your algorithm in general. So how do you actually troubleshoot these things become quite important from the beginning, and I think this is a good time to discuss it. And regularization, quite an important topic. This is what you do when you train models. You try to adopt different, these are like our building blocks. Try to adopt these different methods like weight, decay, and dropout. So we're going to talk about those things more in detail as we move along, and how to actually apply them, when to apply them, and what exactly do they achieve. And then a little bit on forward and backward propagation. There's going to be an assignment. There's actually an assignment already with the backward propagation, which we discussed previously, and how to implement it and this kind of thing. Just to do a research on that. That's why I kind of gave it that assignment. But so there's going to be like a follow-up to that in this one. It's not going to be a really tough assignment. It's just going to be something for you to actually go and try to understand on your own. Because I think it's really helpful. So numerical stability and initialization, as you train neural networks, like I said, there's going to be a lot of work that you need to put in. Things don't really work out of the box, unfortunately, but you can, you have different methods on how to properly initialize your weights and so forth. And these things are really helpful to actually get some stable training in your deep neural networks. And environment and distribution shift, is going to be conversation around that as well, and some examples of these issues that have come out when you're working with data sets, different kinds of data sets. And so, how you might be able to go about and deal with these issues, at least be aware of them. I think it's quite important when you're doing some kind of research or even working on deploying models online, and being aware of the environment you're actually deploying these models on. Okay, so the last one is going to be a Kaggle. So hopefully we have time. I mean, we do have 2 hours, but there's going to be a lot of content. So maybe I'll also try to give 5 minutes break in between, but I could do 2 hours if you're okay with it. Hopefully it's not too much for you. So let's start. So we covered the linearity assumption, right? We discussed this one before. Remember the WX plus B, we discussed that already, and this can be used to do, your linear neural networks, which we discussed previously, and you actually implemented them from scratch, and how to actually achieve it, do a concise implementation as well. But here, we're going to discuss, so what's the weakness, right, of this? And there is some assumption, right, of monotonicity. And this is the case because when you have, like, for instance, an increase in some feature, right, this causes an increase in the model's output if the weight is positive, and also, so it's kind of like really predictable is how your model is going to behave. And sometimes that's good. I mean, for smaller data sets, maybe that doesn't really have a lot of dynamics in it. Maybe it's quite useful just to use a simple model like this one. But in reality, we're working with data sets that have really high dimension, a lot of features, and the way how we're going to fit a model on that data maybe requires more complex relationships or complex understanding of the relationships between features. And so in order for us to achieve that, this assumption and then this linearity really becomes quite weak. And so we really need to move to something more robust. And this is where the the multi-layer perceptrons come in, right? So that's kind of the storyline there. So for instance, if we wanted to do, just to kind of outline here, emphasize on the weakness of this linearity assumption is like increasing the pixel intensity. Oops, what am I doing here? All right. So increasing the pixel intensity helps to distinguish between cats and dogs, right? So imagine that you have this kind of example that you want to train a model like this. Imagine there is some inverted image, right? And if you have this inverted image in the data set, it probably will fail because it's not going to be, the model is not going to be able to, it's not sophisticated enough or complex enough. I will talk about complex and what it means later, but it's not complex enough to actually represent this sort of dynamics in this data like this, like inverted images. So that's something that could be addressed quite easily, actually. Maybe you need to actually include some kind of hidden layer, which actually gives you a better representation and can model features much better, right? So in this case, when you're using like hidden layers, they give you more robust presentations, right? Consider context and more interactions between features, which is what you want to achieve as you work with more robust data sets. All right, something like that. And then there are other examples in the book. I really like the examples in the book, really easy to read through. So take a look at that, but this is just one of the examples. So we really need a way to model the complex relationships that exist in your data set. So how do we actually do that? We may be able to do train a model to jointly learn that representation, right, via the hidden layer. And, at the end, you can have a linear predictor that just acts on that representation, and you get your outputs. So we're going to talk about the architecture a bit of MLPs, but just to summarize what it is, this is just, you can think of it as a simple deep neural network. They're called multi-layer perceptions. It's just multiple layers stacked together, and they're fully connected, okay? So, what is in the middle here, which is the hidden, you can see it in the figure, is, fully connected with the inputs and also the outputs as well. So those hidden layers are basically in charge of learning the representation, and like I said, interaction between features, which is what you are ideally targeting here with this type of architecture. Train high capacity models that can help with the overfitting issue, and we'll talk about overfitting because it's a really important topic. And you will see that even as you use something like a multi-layer perception, you still run into issues because obviously, like I said, the aim is to have that really strong interaction and be able to capture that relationship between those features. And as you do that, obviously there comes many issues, especially as you work with something like a neural network. It's a very unique kind of data structure that you're working with, and it requires some ways on how to deal with these issues to avoid overfitting. So we'll talk about that later on. This one is just, okay, again, here's the architecture. By the way, I reproduced the architecture here. I like using my own colors directly from the D2L.ai book. And here you can see that we have like the hidden units in the middle, then there's the inputs, then there's like the linear predictor at the top, right, in charge of outputting those predictions at the end. And this is just at a high level what it is, just a little bit more on the MLP architecture. And like I said, the idea is to handle more general functions and learn more general patterns. And that's the whole point of it. And by adding, and you can achieve this by just adding hidden layers, right, and stacking them up. Okay, so more on the architecture. So this one, I think this is a great way, if you're getting started, I think this kind of helps. I kind of designed this chart. So this is not in the book, but I try to use the same, figures. And then I kind of just designed this nice little chart here to give an idea on, the dimensions of each layer, and also, what weights are actually related here, and actually the dimensions of the weights as well, and the bias and so forth, right? And what is the output? What does the output look like, which is on the right-hand side. So you can see if we start at the bottom, the input layer, right? You have our inputs. Maybe think of this as an image, maybe, images of cat and dogs. And what we would do is usually represent that image in like a flat vector, right? So once you have it in a flat vector, then that's going to become your input, and you can think of your input. You can see the notation there. if we're representing the entire data set, it's going to be an n by d, right? N is a number of examples, and d is just a dimension of your input. And so you can take a look at it. I won't go through each one of them, but just look at it. I mean, I pulled these equations directly from the notations directly from the book, which is easy to do, by the way, which I really like as well. And I just copied them over, and I try to organize it here just for you to understand. So you can see here in the hidden, what the hidden representation is. It's just, you know, your x multiplied by w plus b, and you can see that that's actually carried over for your output to get your output, and you can see the w2 there and the b2. So you can see how it's being transformed. So as you maybe design more sophisticated neural networks, and you're stuck in more layers, maybe this could be a really good exercise for you, just to see, you know, if you're actually visually getting the idea. So that's why I designed it. So feel free to use that. I will share the slides later so that you can actually use that as an exercise. So with the activation function, notice here, this is really vanilla. Like I said, you're not really doing anything special. Actually, if you read the book, you actually understand that, and it's proven there. If you stack a couple of hidden representations, really you're not doing much, because you're only transforming. You're doing transforming an affine function of an affine function gives you an affine function. So you're really not doing anything special, not yet. But when you combine it with activation function, and you start to use these ideas that have been introduced later on in the field, you start to really understand the strength and power and the capabilities of neural networks. So now you have this activation function, which has a lot of really nice and desirable properties. So with activation functions, definitely helps you to train models much faster and more efficiently. That's one of the reasons why they were introduced. And of course, there are other benefits of this. I mean, if you even try to go and try to look at the reference and try to look at the different activation functions like ReLU and TANH and these ones, you will see that there's a reason why we have many different kinds of activations. They always offer you some kind of benefit, but they're mostly about trying to maybe optimize the neural network to make the training much faster, and they have to have really nice properties, right? They need to be differentiable and these sort of things. And these are different conditions. But as you mix it with some activation function, you definitely, that linearity, of course, is broken. Now you're dealing with something more sophisticated, and you're able to, maybe take advantage of these sort of functions, to learn those relationships that you want between those features in a better way and a more efficient way. That's the idea. So there are many courses online which you can look at, many nice videos online that explain to you, what the activation function achieves, and this is a very important topic to get. But here I'm just kind of slightly introducing the idea. So just to give you more of an idea what they do, right? So again, it really just is in charge of like controlling the flow of information, right? And fires, a neuron fires, and the neurons become maybe important at some point, and it's really this maybe representing something useful in that data, maybe some useful feature that would be used by the network at some point to actually make a prediction. So that control flow of information is what basically the activation functions are in charge of. But there are, like, again, many other benefits as well, as I said, to training more efficient neural networks and training them much faster as well. They are differentiable in nature. That's one of the properties that needs to be met. Of course, these are neural networks. You're doing some backpropagation at the end of the day, so you really need to make them differentiable. And it adds this non-linearity, which is what you're looking for. And this is what allows you to kind of model that complex, those complex functions, right? Those complex functions, because you're really targeting to build a neural network that learns those complex relationships between those features. So, by having this kind of complex functions, you're able to better fit your data. So there are a few activation functions, just to mention a few here, ReLU and sigmoid. These are the popular ones. Sigmoid really is just more like a thresholding kind of function, right? It's actually referred to as a squashing function as well. So it squashes, those activations, maybe those outputs of those layers, and basically squashes those values, so from in a range 0 to 1. And it's heavily used in binary classification. I think we used it previously But here, we're going to start to see more activation functions and the role they play, like ReLU, for instance, that give you better ways to train neural networks. As you move to, say, something like multi-class problems, maybe it becomes more important to actually use something more sophisticated that can address those problems. And in the ReLU, again, you can see here in the slide, it actually helps to mitigate this issue of vanishing gradient. So what is this vanishing gradient? So I'm going to talk about it in an upcoming slide as well. But you can see that these activation functions, they were introduced for a purpose, and we have many of them as well. And we even have many variants of ReLU as well. So that's something that they take care of, the vanishing gradients. We're going to talk about it later on. So it's just more like, the gradients of your network eventually, they become so small that you're not able to really learn anything, and you're just training your neural network. You're not really learning much. We're going to talk about it more later on. Okay, so the other thing is, right, it's very important to actually select the right activation function, right? So that you're able to train stable and effective models. I'm going to talk about it later on. Okay, so the aim at the end is to have this model, or have a model that you're really interested in, this concept of generalization error, right? So that's basically what you're interested in when you're training neural networks, and it's really important to distinguish this from a training error. Because a training error is just the model training on the data and the error that's coming out, right, based on your loss function. But that tells you a little bit about the model, maybe, and maybe the model is actually learning some patterns that are helpful for distinguishing labels, say, in a data set. But if you actually test it on a testing data set, right, assuming that your testing data set represents something, represents data that comes from the same underlying data distribution, maybe it's the case that your generalization error is actually really bad. And that tells a lot about your model. So how do you actually address it? How do you actually deal with this discrepancy? How do you make your model better at generalization error and reduce the generalization error? So yeah, that's something we will cover in the coding walkthrough as well. But that's what I wanted to say here with the generalization. And there's a lot of conversation around this, what it means to actually be generalizable and these sort of things. And there's a lot of discussion around that and debates. But in the end, we want to keep the discussion really simple. We're only interested in that generalization error at the end. And we need to employ different techniques like regularization to avoid things like overfitting, because overfitting, you'll start to see it is the case that when you have overfitting, your training error and generalization error, there's some huge discrepancy there. And usually that's because of overfitting. And how do you deal with it? That's the question. So here we have a slide on, this one is just talking about generalizability, model generalizability, and some of the factors that affect them. Obviously, this list is quite short, and I actually even kind of omitted a few things mentioned in the book. But the main ones will be, these parameters, right? If you have too many of them, too many features, that could lead to overfitting because this really makes the model too complex that eventually doesn't really, you would have to probably reduce the complexity. And there are many different ways you can do that. Similar with the parameter values. So the values themselves for the parameters are quite important when training. Remember, you're always doing this, calculating those gradients. And as you calculate those gradients, if they're, maybe too small, maybe you're going to lead to something called the vanishing gradient problem. Or if they're too big, they explode, and you have a model that really it's not usable. So it's really good. It's really good to think about how do you actually control these values, right? How do you have this control over those values, and what kind of methods you're going to use to actually take care of that? And there are different ways to deal with that. And there's a slide specifically for this one, which we're going to discuss, because obviously those values, they eventually, like I said, if they're not in the proper range, they may lead to overfitting as well, because maybe your model again increases too much on complexity. The same one with the training examples, really important, right? One of the things that I learned earlier on when venturing into deep neural networks at the beginning, I really didn't understood, what's so deep neural networks for me were just another model, right? That I could just like apply on my data. And at the time, I was using really small data sets, and I could never understand why my deep learning model was not doing good or better than the models that I were using before on those small data sets. But it happens that with deep neural networks, the more data you have, actually, the more it benefits this type of models. So that's something that's really general, and everyone, accepts this to be the case. So you always, the more data you have, in better hands you are when you're using deep neural networks. If you don't have enough data, sometimes you have a small data set, say something like thousands of data points. Maybe it's even, it doesn't even make sense to apply a deep neural network. Maybe it's just the case that you could actually employ something like a naive Bayesian classifier, something like that, depending on the problem you're working with. But this is something that to keep in mind. And what you see nowadays with this particular one, so with all these three things that you see here, so there's different lines of research that are happening already. How do we actually deal with these parameters, right? What are the methods we're going to use to actually get this parameter and have more control over those parameters and deal with those vanishing gradient? Like you said, vanishing gradient, ReLUs have a lot to do with that. ReLU activation function have a lot to do with this. And so they help with this one. And with the training examples, you see methods like data augmentation methods now being introduced to help deal with these issues. So these are the common issues that you would see, right? So how about model selection, right? So when you're aiming to, maybe you are training a couple of models and you really want to compare them, and you want to understand what model is the best one to choose out of the ones that you are comparing. Maybe you wish to use a model in production, or maybe you even wish to use a model, the results of a model to report them in a paper or something like that. This becomes really quite important. So when you're experimenting, how do you actually choose that? What kind of hyperparameters you're going to use. Also important to distinguish between the different family of models that you're using, the architectures, and so forth. So as you work with different models, you will start to see different things, like I said, overfitting on the test data, right? So that's something that usually comes up. And we need something like a validation data set to really understand, if you're working across models, this will help you to determine if those hyperparameters gives you the best model. All right, so a couple of things here. I apologize in advance if you think the slides are too heavy in text. Why I did this is, I wanted to make sure that I summarize the most important points. Obviously, the book has a lot of material, but I just want to highlight like the most important points. And if you're going through the book and you feel a little bit already too exhausted, maybe the slides can give you a little bit of pointers. And that's the idea that I try to use here, give you an idea on what are topics that really matter out of all the ones that were mentioned. But generally, I don't have a lot of text like this. Actually, I don't like to use a lot of text like this and bullet points, but I think this is the best approach for now. But as we move forward, I will start to reduce the text and just focus on the main issues a little bit and not too much in detail. Okay, so, and then of course, if data is scarce, this is the one I said, you may need to use the K-fold cross validations. So read on that. It's quite really important topic, I think, for when you're doing validating models. I mean, if you have smaller data sets, like I said, probably doesn't make sense to use deep neural networks. But if you want to use them, maybe the way you actually perform the validation is going to look a little bit different. Because you need to have a more reliable way to validate on the data, and maybe you can use something like a K-fold. So you can read more on that. I think it's really important to know that. All right, so a word on underfitting and overfitting. And I really like this figure. I think this figure really illustrates exactly what's going on. So if you could see on the X, there's model complexity. On the Y, there's the loss, right? And you can see that as the model becomes more complex in general, you have this case where the training loss, well, ideally you want the training loss to actually reduce, right? But you have the generalization loss. Okay, it's going down, but at some point you have this optimum, right? Optimum point, which is what you as a deep learning practitioner are looking for. And that's a lot of the work is about this, right? It's actually looking for that optimum point. And then eventually, the generalization loss just kind of again increases, and you have, like I said, when you have too much complexity in these models, then you're going to have that scenario where you have generalization loss just blows up, but the training loss is still reducing, and then you are trying to understand what's going on here. Well, with overfitting, this is the case, right? You have you have a too high capacity model that you actually need to work on and try to reduce. That's why you have methods like Dropout and these different regularization methods that help you deal with this and kind of stabilize your neural network as it trains. Right, so underfitting, there are many courses on this. You can read. There's a lot of courses. I think Andrew Ang has a really, good course on this topic. I really like how approachable it is, at least. And you can definitely take a look at that to better understand. And he goes through a few examples, and he used a lot of figures, which I really enjoyed, and I learned a little bit on that. At least his first machine learning courses had that. I don't know, the deep learning courses, the newer ones, if they do have this topic, but I think it should, because it's quite an important topic. But I really like his chapters on these topics. So you can take a look at that to get a better understanding. And he offers also, ways on how to deal with overfitting and underfitting as well. And you have I think there's a table as well on different things you can try and different items. So definitely take a look at that. I think in the book that we're covering, there was some discussion around it, but there's not a lot of, as I would expect, there's not a lot of conversation around it. There's just a one chapter, and I think you really require some understanding of this, and I think maybe an introduction to machine learning course will be useful here. All right, so with underfitting, this occurs when you have this training and validation error are substantial, and there's a small gap between them as well. So that's a case of underfitting. So so the training error and validation error, they're kind of high, and you have this small gap in between them. So something is wrong with the model. What's going on? And that's usually a case of underfitting. Maybe your model is not complex enough. Maybe you need to add a few layers or something like that. And there are different ways you can deal with this. And then overfitting, which is kind of what the highlight of the chapter, I believe, and all the methods you learn here in the chapter, like regularization method techniques, gives you ways on how to deal with overfitting. It's the most common problem when working with neural networks. So you definitely need to understand it, how to apply these different techniques. So it happens when you have this training error, right? It's significantly low, as you see in the figure, but then your validation error, right? The generalization error, which you're interested in, the validation error is kind of all over the place. Maybe it's too high, and then you want to understand why that discrepancy is going on. Then usually it's because the model is overfitting, and then you have different ways to solve it. You can use a regularization technique like weight decay and dropout. Then or you can actually maybe focus on getting more examples if that's something that you can afford and if the time permits. And then of course, if the model is too complex, maybe and you don't have enough data, usually that leads to some overfitting problem as well. Okay, so these are the two methods, weight decay and dropout, which I will focus on. I think the book does a really good job at this and explaining these two. And you will see how useful they are to deal with overfitting. So let's go through the first one. What is this weight decay? A lot of text, don't worry about it. Again, this is to try to summarize the most important points. But the weight decay is quite a simple concept. What you're really doing is, and what you're really interested in is in shrinking that weight vector. You want to keep that weight vector small. You want to make those values in that weight vector really small. And this gives you, some benefits, of course. And as I said, it does help to address overfitting, right? And this is really regarded as one of the most useful regularization techniques out there. And I think even some toolkits already kind of by default use weight decay because it's so important to actually, it's so useful and beneficial. So why not just use it by default? But the idea is, it is talking about this L2 regularization, which we discussed previously as well. And the idea is to actually add a penalty term to the loss function. So you can see the penalty term here in the equation on the bottom. And that penalty function, really what it's gonna do is gonna, when the model is learning and is trying to update those parameters, really what it wants to do is, if the focus is to actually get those, if you have a problem with overfitting and you want to do regularization, the focus is to actually, like I said, reduce the weight vector, make it a bit more smaller. So how would you achieve that? Well, use the L2 norm, and that's what you see here in the equation. And again, is to shrink the weights. And if you put that as part of the objective, then it's going to tell the model, well, it's really important for us to actually reduce those weight values, and we don't want them to grow too large. And that's kind of the idea with weight decay. There's a lot of theory around weight decay and why it's a really principled approach and why it actually works, theoretically speaking. But generally, the idea is that you want to take advantage of this L2 regularization that you see at the bottom. Again, you can see here the last statements. Larger weight vectors means that learning algorithms should focus on minimizing the weight norm, right? Okay, so one question that usually arises is, why don't we just add, well, we're using L2 norm, but why don't we just add the L1 norm? And there's a discussion about this in the book. I think it's quite important to understand the difference because you can actually use either one. But why do we use one over the other one? That's the question that usually we get a lot. And these two have different purposes. Of course, they may end up giving you good results at addressing those issues like overfitting, but at the end of the day, they behave a little bit different and they give you different properties. So the L1 norm, right, really it's focusing on, so it's trying to minimize the effects of some features. So basically it's almost like a feature selection. When back in the days when you had to design your own features and you kind of wanted to figure out what are the best features for this particular problem. So something like that. It's almost something like that. It resembles that sort of thing. And then the L2 norm, so that's the L1 norm, and then the L2 norm is more, one of the things why L2 norm is actually considered better than L1 norm is because it's more convenient computationally speaking, and it's much easier to actually obtain the derivatives. As you can see here, we have this kind of, we have a squared, and we can easily deal with that when we're dealing with derivatives, and we spoke about that. That's why it's actually more convenient as well. And then other benefits, I would think that the idea of this, like, again, you're actually trying to tackle that weight vector, and you want to kind of control the values that are being learned on those weights, and because obviously you don't want that vanishing grading or even that explosion of gradients as well, like we said, and so you want to kind of have more control over that. And so with the whenever you do a weight update, you're also considering that shrinking of size of the weight vector towards 0, right? So you're actually shrinking those values. And that's the effect you get with the L2 norm. That's the whole idea of this one. Let's see, what else did I miss here? Yeah, so it's just going to penalize large components of the weight vector. And you can actually do this, right? You can open like a notebook and try to figure out yourself, just use like dummy values for all these different variables that you see here, and then you try to see what's the effect of the update and what it's doing. It's really easy to test this one. And I think one very important thing is that you're trying to basically distribute the weight, right, across the features, because some features become really way too important, and you really want to minimize that. But there are other ways also that you minimize that as well. And dropout is a good way. Actually, dropout is quite similar to weight decay, and you will see in a couple of slides that are coming up why this is the case. Yeah, so this is a slide right here. It's another technique, right, for regularization, dealing with overfitting. It's quite similar to weight decay, at least from a theoretical standpoint. It behaves quite similar. But you're really, what you're targeting here is you want to have some simplicity, and in simplicity can be represented by smoothness. And how do you actually achieve smoothness? You actually need to focus on making sure those neurons in the layers that you have, the hidden layers, and that they become less sensitive to some activation of maybe, say, a previous layer. Because when you have these things occurring, so you have this behavior occurring between the layers, what happens is that you're really just learning some kind of association, and you don't really want that. What you really want is you want this model to actually learn general patterns. That's what you want. You don't want these associations, this kind of spurious associations that the model is learning, and you want to kind of break that. And so you can see here at the bottom being defined. So you want to break that co-adaptation that happens between the layers. And that's the whole point of it. And so you want to add some kind of noise. You want to add some kind of randomness there. And it's quite an easy thing to implement. And that really helps with, with disabling this co-adaptation, like I said. So let's see how that looks. So this is the code. I actually took the code directly from the book. And this one is really telling you how you can actually apply it. So you can see on the if you focus on the code, again, you're just kind of injecting some noise, debiasing some layer, and the way you achieve that is by zeroing out a hidden unit with probability p, and then you kind of normalize it using a fraction of nodes retained, which is you can see in the equation here at the top. Don't worry if you don't understand that equation. It's not quite important right now. But if you look at the implementation here in the code, and that's why I kind of pasted it here, it's quite easy to understand. You can see here, it's how it's illustrated. You have this kind of, and this is really good, right? I really like this example because it's an easy way to actually test and to see if your understanding of what's going on here and what this technique is actually doing. So the way the book, people use different examples, but the way the book focuses on is the uniform. So you're sampling from a uniform distribution. And once you have that uniform distribution, what you do is you say, well, if there are values in this particular tensor, or elements in this particular tensor that are above this dropout value that I provided. So this dropout could be, something from, say, that ranges from 0 to 1, say something like 0.9, right? You're going to see, for instance, if it's 1, right, that's the maximum one that you can actually apply. So if it's 1, what it does, it's, all the elements will be dropped out. That's the highest you can do, right? You can achieve. But maybe you want a balance. Say you want something like 0.5. What it's going to do is just going to, zero out, 50% of those units in that particular layer. So you can actually visualize and you can see for yourself how this works by this function. So pay attention to this function, try to implement it yourself and try to understand it, play around with the values, plot the values and see what's going on here, because it really helps to understand. Again, different lecturers use different approaches to visualize this, but I think this one is quite easy to understand. You can see here if dropout is equal to 0, elements are kept, right, because your dropout value. And sometimes you see people use like keep prob, right? That's kind of the inverse, but that's the same idea at the end of the day. Okay, so let's see. That's just what I wanted to say here. But you can read more in the book. That's the whole idea of it. And that's the idea of dropout. Dropout is just kind of, you are going to zero out some units because you, like I said, you don't want to learn those associations, spurious associations between the layers. What you want is to learn general patterns, and you want that to be a little bit, you want to have a more like random connections in those between those layers. So here, what you have now is the intuition is, of course, you have on the left-hand side, you have more like a complete neural network. And then on the right-hand side, you have, you're missing some variables there. You're missing your H2 and H5. But, on each iteration, a different set will be selected. And this allows for some, like I said, injecting of that noise. And that's basically what you're targeting with this. And so you have that, you have those like strong associations that would be dealt with, that usually the neural network will pick up on, and you are dealing with them by using this method. And you want to learn more general patterns. Okay, so let's see. And again, the note here is that the respective gradients also vanish during broad propagations. Quite an important point when you're implementing them. And this method, it's good to understand what it's doing, but A lot of the toolkits that we use today already have, how to actually apply Dropout, and you will see a lot of models that are implemented online already use Dropout. But just understanding intuition is I think it's already enough. You don't really need to implement it on your own. So this is the forward propagation. Again, the book has this figure. I just reproduced it from the book. You can see it here. And it's really good to know like how the information flows. Of course, you have your X, W, right? You have some multiplication operation here. And then you have your Z variable, right? And then you apply some kind of activation function. And then, you got your H variable and so forth, right? You're doing this and it's like a computation graph. It really gives you a good understanding of the operations that are happening in the forward propagation step at least. And then I think one of the assignments that I want to focus on here is this. So I basically just copied and pasted here the figure. What I would ask you to do here, for those of you that are going for the certificate and are doing the assignments, is to plug in, right, the equations. So there are equations in the book on how you actually get to all the important calculations that you need for doing the backward propagation and getting those gradients. So try to plug them in here in the same figure and try to actually use the arrows and how the information flows back. So again, you can look at courses online. There are so many courses. I think Android courses, they cover this as well. But just to give you a little bit of an assignment and a challenge here, try to take those equations and plug them in the same figure that we have here, and just using the same convention that the book is using. So if you can do that, that will be great. If you can't, don't worry about that too much. But we will have a solution in the next when I deliver the next session. I will have a solution for you. Okay, so stability, numerical stability, initialization, very, very important topic, I think, in my opinion. Initialization, right? So we initialize them randomly, those weights. That's what you typically see. And really, we don't, well, researchers are actually trying to understand, different ways to understand what is, better initialization of weights, right? And that's an ongoing research, area on its own, right? And well, for initialization, at least why we care about it is because, we want to have stable training, right? That's what we're focusing on, to have some kind of stable training. And if your initialization is bad, well, your model is at some point not going to learn anything, or, it's just going to get stuck in learning. So that's why it's really important to understand good initialization methods. And there's just a bunch of them. Toolkits actually have these built in, different ways you can actually employ some kind of initialization techniques. So many of them, right? And many others are being introduced, and different methods are being introduced to do initialization and actually have some kind of more numerical stability in your network. Because again, we're really, really interested in creating, training a model that's, that's stable during training, and we don't lead to that vanishing and exploding gradients, which we want to avoid. So it's quite an important topic again. Okay, so the good thing is, right, we have all of these different components that we can use. So we can use the activation functions, it's like a building block. We actually combine it with initialization in different ways. And you can look at the book. The book explains how you may be able to achieve this. But this is what I think is really interesting of neural networks. You can actually use different methods, techniques, and combine them and actually come up with the most stable model when it comes to training. Okay, so important because, of course, unstable gradients, they lead to unstable optimization algorithm. We know that. If parameter updates are too large, they basically destroy the model. If parameter updates are too small, they render learning impossible. And we covered the weight decay, which is one of the techniques that you use to deal with this. And that's why here you see that we have all of these different techniques: initialization, proper initialization, the use of activation functions combined with something like weight decay or dropout, all of the different ways to ensure that the model is actually learning in an optimal way and it doesn't get stuck in learning. Okay, so the distribution shift, right? So when you're deploying models, right, you're deploying models, let's say in the wild, very different environments. And also, of course, you're working with data that could be in different distributions. That's something you really, really need to pay attention to from a data set standpoint. You don't just grab a data set and just train a model and expect that on the testing data set that you have, that your model does well. It could be the case that your testing data set that you have kind of put aside has some kind of distribution shift in terms of labels, maybe the distribution of the data itself, like the features. And you really need to do some analysis on this and try to understand, because in some cases, right, this could be the issue when you're training a model and you're like, why does this model do well on the testing data set? Well, it could actually be because of the distribution shift, and not really the model itself. So understand the origin of the data, right? And what you really want to do with these model outputs, because let's say you really train a nice model, it does well on the validation data set, and then when you put it, say, on some kind of service that you have out there, your users are complaining, hey, the output that I'm getting, it's biased, it's not doing the right thing, it's outputting something that is crazy, it's not really doing what I expect it to do, and that's because maybe the data that they're plugging in is, it's quite different from what you train your model on. So that's something to take advantage, to really pay attention to. And you can see there's so many cases, right, of this in the news. You always see all of these different news that are being reported. For instance, like last month, I think we had this issue with the, I don't know if you heard it, but it'll be interesting to take a look at it. I think there was some kind of test. They were trying to create, I think, a grading system, something like automatic grading system, and it was trained on grades, on the data from students, on grades from, say, a different school, and then they were trained to apply it to a school. So it's a whole mess, and usually it's because of this. And so it's those examples really, it's a shame that they happen, but this is the reason why they happen. So read on that, quite an interesting one. And then here, what I want to say, there are some concerns, obviously, when you're dealing with these things. In some cases we have very simple models. They don't do so well when you put them out there, because maybe what you were interested is just to have a toy example, and you thought, oh well, it does so well, and then you want to put it out there, but it does terribly. Sometimes models are too technically difficult as well. That's another thing to think about. And of course, ethical issues with these algorithms, right? They may convey some biases that you really don't want to happen with your models. So another example came up like a couple of weeks ago as well, where somebody had like a gender prediction model and they put a website online. I'm not going to mention the name, but it was a disaster. I mean, you really have to think about it, like how you want to apply these things in the real world, and you really need to think about it and understand these issues like distribution shift. So the types of distribution shift, just to give you a high-level overview, let's see, I already spent almost an hour here, but I'm just going to move faster because I have this coding walkthrough, which is going to take some time as well. And I hope to finish and try to show you like the Kaggle competition and this sort of thing. I think that's important to get some hands-on practice. So the distribution shift, just go through the slide really quickly. You have the covariance shift. These are more about the features, right? The features may be a little bit different. I mean, you have, say, some testing data set that you have on the side, and say your training data set, but your feature distribution is quite different from the testing data set. And an example of this could be where you have like cats, you have realistic images, and then with your testing data set, you have things like cartoons, representation of these images, and so it's gonna give you really bad results, and you're trying to understand why. Well, this is the case, and that happens a lot with online applications. I mean, especially when you have applications that depend on camera, right? So it could be the case that someone is, snapping a photo or something, and they want to classify it, but maybe they're snapping a photo that's, the data is actually in a different distribution. So it's going to be a complete mess. So all these things, just think about them as you become a practitioner or a researcher. These problems are good to have at the top of your mind. The label shift as well. The label is just more about the labels, not about the features. But there could actually be a shift in the labels. And there's some good examples, especially with disease. So I actually work on this type of research as well, and that's something that I observe. I could never actually put a model like this. And actually, if you look around and you read news and you read researchers in this space, especially with related to medicine, you realize that these models are really hard to actually put online in production because you have so many different, well, with this kind of data, you have so many different things. Like, when you're dealing with diseases, for instance, the symptoms always that change, right, across time. And the diagnosis could also change. So you have this like really high variance going on there. And so, they're much more difficult to deal with. And the book explains some more examples. And then the concept shift, this is related to the labels as well. So you could have, say, for instance, with the mental illness, I actually observed this in my research. I tried to do some diagnosis on I think it was more bipolar and people that are not bipolar, at least on social media. And then you have, you could have a case across if you consider like, temporally speaking, someone can actually jump from a bipolar state to something like an anxiety state, but you're actually not modeling that, right? You're actually not paying attention to that. So how do you actually consider those things on your training models? And this becomes even more important as you try to think about real world usage of these models. And that's why I really like that they mentioned it here. So ongoing research is going on in these three areas as well. You can learn more about that in the book as well. So I think this one is a good example, a very common example, actually. You can see here in the figure at the bottom. I don't know if you have seen it, but in the US, we have this strange thing where, the soft drink name, depending on which area you come from. So you can see here, like at the top towards the north, like people can name it pop, which is actually a really interesting phenomenon. But you can imagine that this is about influence and this sort of things. But across time, it's really interesting to see what's going on because, geographically speaking, you will see that there is actually some pattern, right? So at the top, you see that people refer to it as pop. At the bottom, towards the south, people actually call it just Coke. And when you go to these different places, you get confused because you don't understand what's going on, why people are referring to drinks. And this is very common with foods, by the way. If you go into some literature that's are doing some kind of data analysis on food related subjects, you will see that this is very, very, very common. So not just with drinks, but in general with food. So really interesting stuff. Learn more about it. I think it's really useful to know it because you're going to experience it at some point when you're dealing with these models and these sort of data sets. So this one is more like, these are the topics that are going to come up. Well, once you understand the distribution shift and these sort of things, you could have different settings. You could have batch learning, right, where you train a model, you deploy it, you never update it again, something like that. And then you have online learning, which is you need to continuously improve the models. So there are many books that talk about that as well. And we're going to talk about bandits control and reinforcement learning, which is a really, really interesting topic these days. So this will be left for later on. Okay, so announcements. I will post a recording of chapter 5 in the coming days. It was going to be impossible, as I kind of predicted. It's going to be impossible to actually do it together with this one. And I hope you really got enough from the slides. I mean, take a look at the slides again, go through them. If you don't understand something, you can always shoot me a question or shoot it in the chat as well. And you can do your own research as well. So hopefully it was really helpful for you, at least the slides and what I kind of try to summarize. But in the next chapter, I'll try to make a recording because we won't have a chance to actually do it live. And hopefully the recording is useful for. I think this one we can afford to record it, and we don't have to do it live because it's mostly just going to cover how to use GPUs and this sort of things as we move along and we try to train models much better. So next week we'll have Samil Chamlal. He's a PhD. He's a deep learning instructor in NVIDIA. He's going to talk about CNNs and modern CNNs. So quite excited about that. Definitely looking forward to this. And that's going to come next week, right? So CNNs, really, really useful CNNs for dealing with image type of data. Actually applies to text classification really well as well, from my experience. But we're going to learn more about those things as we go along. All right, so demo time. Let's try to do a demo here. I only have 1 hour. So I'll just look at the questions and see if you have any questions, and then I'll need to run this as I take some questions. Okay. All right. Right. So let's see. Yeah, so the generalization error, not to confuse people, depending on what setup you have, right? So sometimes, you cannot afford a validation data set. Sometimes you only have, a training and a test. So basically, it's like what has one says, right? Generalization error is a measure of how accurately a model is able to predict outcomes for previously unseen data. So the unseen data is really what matters here. And unseen data could be whoever you have it set up. So yeah. Okay. Yeah, and yeah, probably did a mistake there. Yeah, that's my bad. But yeah, the definition is more clear. Okay, so all right, so okay, let's see if I have any more questions. Yeah. Okay. All right, I'll move on. So there's a question from Josh. I think maybe it's about GANs. Maybe you can take that question and maybe ask me later. I'll try to give you an answer for that. Yeah, but I think we're moving way ahead because we do have a section on GANs too. So maybe you can save it up and we can address it later. All right, so let's move on. We have 1 more hour here to deal with the coding walkthrough. Let's see. Okay, so just make sure again, the credit goes to all the authors, and the contributors are contributors of the D2L.TI book. It's very important. All the credit goes to them. So I'm just kind of using their code. Okay, I'm installed all the libraries here. Right, we're gonna even use pandas too in this one. Here, let me just try to enlarge it and make it widescreen. Okay. Right, so we're using PyTorch, and this one just shows you more like the activation functions. Play around with the activation function. Actually, in the first lesson, I shared a notebook that I prepared myself that goes through all the different activation functions, and explains how do you actually go about, doing the the derivatives of those functions, because that's something that you have to also understand. So try to do that as well. Sorry, the gradients, right? So the gradients of the activation functions like ReLU. And so this one just shows you a little bit on that, like gives you an example of how they behave. So if you have some kind of X input, what will be the result. And actually here in the second one, it tells you, how what it achieves when it actually calculates the gradients. So you have some kind of X input, then you have the result looks something like this, right? So for mostly for zero related values, you have this kind of like this kind of vertical line here in the middle. So for negative values, you would have so you have it at 0, and then for positive values you have 1. So that's what the ReLU is doing. So go through a couple of examples yourself and try to understand what it does. I like the examples given here because you can easily adopt them. Try to understand your activation functions. Try to look at the different variants of ReLU as well, and try to see how the data is being transformed with the activation function. Okay, so yeah, I want to just keep this. Let's go into the perceptrons. So here we have, let me see if I can run this code. I thought I did run the code, but something's, it's probably still running. Hope not. Yeah, you can see it's a lot of code. All right, so let's go back up. Let's see. Wow, it's a lot of code. All right, so we have our data sets. This one is using the fashion MNIST, and we're gonna do a couple of things. First of all, we're gonna just test a simple model. So the initialization we set up before. In this case, we have kind of like a hidden, and then we have this output layer. These are the parameters corresponding to that. If you cannot follow along with the code, take a look at the table that I have on the slides. That will help you a bit. And then you have the activation function, which is implemented, right? It's just doing a max out of the input that is here. If it's, you can see the behavior here, right? So you can see the value. if the input is above 0, it's going to give you some value like this. If it's less than 0, it's just going to give you 0. Okay, so you can see here. All right, so that's the value. And so here we are very important point. So we want to come up with your input representation. So you want to flatten the vector. So this achieves that. You can see the line of code. This one achieves it. And this is basically your model, very simple model. You have some kind of value, and then you output that, right? So you can see the table again. The table helps to follow along here. You can see the special notation here, right? That's just a matrix multiplication. Then you have a last function. You have a model last function. Then you have a training, and then we are just relying on the D2L package here. We spoke about the code in the previous session, and you can see that you can easily train a model, pass model. You do remember the data loaders, training, testing, your loss function, number of epochs, and the optimizer. The optimizer is SGD, and then you have here also the learning weights and support. Let's see. So we go through that, and then you can see here the results. Right, so if you look at the results, by the way, we're using cost entropy loss per loss function. You can see that the training loss is going like this, right? Good, but then and then you see that the let's see, training loss, yeah, it's going down, and then training accuracy and testing accuracy are going up. That's good. That's generally what we want to see. Okay, and okay, let's see. So, and you can see that when it evaluates the model, right? It's really doing well at prediction. That's just testing. Okay, so let's try another model. So here we're going to talk about underfitting, overfitting, model selection. So you can see that we have some kind of function here that we use to actually come up with the y. And so you can see here that we have, I think it's a polynomial, yes, it's a polynomial, and then what you want to do is, I think in the book it explains that you may want to, so if you test it with something like this, maybe it's a little bit too complex, and maybe you want to reduce that complexity, and you're going to have this overfitting behavior. So it's just going to illustrate that for you. So this is mostly like just synthetic data that you're using here. So we have the maximum degree of the polynomial, and then some training data, and then let's see. Okay, so this one is doing that, and then at the bottom, I'm not going to go through all the code, but just to explain to you what it's doing at the high level here. All right, so that's going to be it. So that you have the number of, I think the number of examples, and then the features, 20, and then I think you take a few of them, right? Yep. So you take a few of them, and you kind of print them out here and try to understand what it contains. I think that's what it's doing. And then it's converting the NumPy arrays into tensors. So you can actually really easily do that with this storage tensor. You pass in the your x. Let's see if that is the case. I think it should be, I don't see x here. All right, so it's a list comprehension. Yeah, this is the reason why list comprehension sometimes is hard to read. So it's a list comprehensions. You can see here that it's going iterating through each one of them, and it's kind of coming up with the with your true parameters, those weights, the features, and the polynomial features, and then the labels. Just coming up with all of those, and you can actually just print them here. Okay, so then you want to evaluate the loss, right? So you remember the accumulators; those are good if you're going to track some metrics. So we explained that how it works. It's just a class that's in the D2L library, and then you kind of just go through this, and then you're obtaining those metrics. So you calculate the loss there, and then of course you're going to train, right? All this code, we have seen it before. Your model. your loss function, right? So, and then of course you're maybe doing some extra transformation here as well, right? You have your loaders, data iterators here. Then you have your trainer, which is optimizer. And then, of course, animator is just going to animate what's going on. And then you go through epochs and so forth, okay? And then you train. And then it's going to give you all the metrics that you want to take a look at. Okay, so for the third order polynomial function here, polynomial function, you have, okay, how can you select them? So you can see here, if you're, how to deal with arrays and these different data structures, you have to understand what's going on here, right? The ranges. But we want to first pick the first 4 dimensions so you can see what it's actually selecting. And this obviously was, so you can see that it's actually doing some normalization here as well. So just try to look at the code at the top to see how that's being done. But that's actually just a pattern that's going to happen here with all those features. Okay, and here it shows so that's passed in, right, as the features, and then you can see how the model is doing. So you can see that this is a training loss, and then this is the testing, and you can see how it's kind of converging in the training. So it's just showing you that example, really simple example. So if you pick 2 dimensions, right, you can see here that it's the training and the test. Of course, the losses are together over here at the top, but maybe they're not, like we said, right? If there's some, if the errors, the loss are too high, and there's not a lot of discrepancy between them, something is really going on here. And it happens that because we're using a linear model, there's some underfitting going on, right, with this particular one. And again, it could be the case because we have this kind of third order polynomial function, but we have a very simple model, which means that it's going to underfit, which means that we probably need to use a better model for this type of features, right? So maybe to capture those nonlinear patterns. So you would definitely need to model this, but the linear models are not able to actually do it. So that's what the code is showing. And so here we have, and I think it shows you some examples, some more examples. So it shows you a case of overfitting, which is great. Again, you can see, I think this one picks all the dimensions. So now it's like really complex, right? Really complex because it's using all the polynomial features. And you can see that there is some discrepancy between the test and the train loss. So in this case, maybe there's not enough data, right? And we probably need to provide it more data. So again, play around with these examples and try to see if you can, replicate these different scenarios where you have like really high, maybe say high training and test loss, and then like we had before, and just play around with it and play with the different polynomial features, and you can actually see the trend. So that's what it's showing you. All right, so, and then of course it gives you an example of weight decay, how to actually implement it. Gives you another example here. This one only has 20, and then you kind of initialize parameters. And then of course here is just like more like the L2 penalty, right? That's the penalty term on the loss function, and that's how it's implemented. It's quite simple to implement. And then we use the same linear model. I'm glad I have these notes here because this is a lot of code, and I don't remember all the code as I was putting it together the past few days. But I'm glad I have these notes. But the code is quite simple. Actually, the code doesn't change a lot. For all the examples, the code is not really changing that much. In some cases, I'm using maybe a function like this, or say an additional function that I provided here. But in most cases, it won't change that much, at least the structure of it. Okay, so we have, the code looks pretty similar to before. And then we have some kind of evaluation. And then here we have the results. So this one tests without the weight decay, right? Without adding that term. And you can see how right? The loss is going like this, so it's going downwards, but you have the test never changes. So what we said about this scenario, well, we said when there is this like huge discrepancy, something is wrong, and then that's a case of overfitting, right? The test is way too much than the training error here. Okay, so now to see the effect of weight decay, because the weight decay is one way to a technique to tackle overfitting. You can see here with this simple example that we came up, we can see that already it's doing a lot better, right? So you can see that the train loss goes like this, and then the test loss is going downwards, which is what we want to see. And that really tells you. So I like the examples because, I mean, if you have never trained a neural network before and you see these charts, you see these plots, and you really cannot understand what's going on, I think these examples already give you already an idea of what's going on and how you may be able to tackle it. And the good thing is with these toolkits, you don't even need to implement weight decay, as you will see an example later on. You can actually just, with one line of code, you can actually adopt it yourself. So this one shows you that. So you can use the effect of the weight decay by simply, because we have, this is just a PyTorch model, but you can pass in it as a parameter, right? You can see here we're doing this in the optimizer, and you're dealing with the parameters, and you're telling it, okay, you want some weight decay on this, but we're not going to apply it to bias in this case because we don't really need to. But we're mostly focused on those weights, okay? So, and you're going to apply some weight decay. So that's cool. That's really easy to implement. You don't really need to implement yourselves because maybe your implementation is not that efficient. So that's something to always take into consideration. I always try to use the ones that are built in. Okay, so I think it's the same. Most of it is the same, right? You see the epochs iterating through this iterator here, and then it's just doing a training, and doing some backward calculating the loss and support. The usual stuff, and then here it shows you again using this the built-in functionalities of PyTorch and applying weight decay. You can see here that if we do it without, so we just pass in 0, right? What is this function? You can see train point size WD. So WD is what you pass in right here. Okay. So in this case, we're just disabling it. We're doing without weight decay. And you can see here we have the same problem as before. This is an overfitting issue. And then once we apply it, we just apply the term. Remember this term here with the weight decay? It's the let me show you again. This term right here, and this basically tells it, what's the effect of it. Okay, so how strong should the effect of this particular solution that you have should be applied to the to the objective here. And you tune it. Of course, you try different numbers here. You could try something like 4 or 5, and you play around with it. And this is how you experiment. I think with toolkits these days, this is very easy to do. You don't really need to do it this way. I think this is a lot of manual work, but it's just showing you the examples, which is already interesting, and for you to actually study and understand what's going on. All right, so and later on you will see that these things are actually already implemented, and you don't really need to do all of this with the examples that are coming up. So you wanna maybe observe the regularization effect, and so let's see. So this one, oh, this is the same one. Oh, sorry, that's the same one. Yeah, I'm keep going up and down, but that's the same one. All right, so the weight decay, and then let's try the other regularization technique with the dropout, right? So this is the one we covered in the slide, right? Read this and try to understand what it is. Different people actually have different implementations for this, but I like this implementation. It's pretty clean, and you can easily understand what's going on. What's the dropout, what it's doing to whatever it's being applied on. And of course, we depend on the samples from the uniform distribution. But I think it's quite easy to understand what's going on here. And I kind of print out some tensors. So imagine the first case. So we have this kind of random. So we have a range, so from 0 to 15, right? So we have all these values. And so let's say all these values were being passed and to this dropout function. And then of course, if we So in this case, we provided 0. What is 0? 0 is a dropout. And we say if it's 0, right, all the elements are kept. Basically, it's just going to return the same thing, right? You can see here the effect. And if we do 0.5, now that's a probability 0.5, what's going to happen is that you can see the effect really right away. So you can see here that we pass the same, right, the same x, and then it's going to do a mask. I actually printed out the mask, but so just to show you. So it's going to, you know, how much of it is going to mask, it's going to keep and it's going to throw away. So how much? 1, 2, 3, 4, 5, 6, 7, 8, 9. So it's going to try almost half of it, and then it's going to keep almost half of it right there. So you can actually see what's going on with that. And then, of course, this is a result. You have this kind of normalization going on here. And so you can see that the values here are not the same that are being returned, but you can see that it's already applying that operation. So I think it's useful. It's quite useful to understand it, that you could go through the examples and you can try more and more examples. And when I did one, of course, it's just going to do it on all, and it's going to just return all of them as 0. So that means everything was completely ignored. All right, so how do we apply this sort of effect? We said this is really useful for avoiding of learning those associations. Mostly we want to learn general patterns, and we want to avoid those sparse associations. So how do we actually implement and apply this? Well, we don't need to implement, like we said, most of these things are already implemented and they're built into these packages. You can directly use them. So here, take a look at this example. So far, we haven't seen implementations like this. But this is the when you use something like PyTorch or TensorFlow, this is what you're going to see, right? So far, we have just been implementing things using the sequential module, but you can see here that we're actually implementing a class, and we're defining some important information here, like the number of outputs, number of hidden, and these parameters are used to actually define the layers of the model that you're implementing. And then here you have your forward propagation, what's going on with each step. Right, and try to understand what's going on with this. If you don't understand this one, it will be really, really hard for you to understand the examples that are coming up, because most of the examples will be represented this way. At least they will be coded in this way. So try to understand what's going on here with this format, because this is the convention that's being used in the community. Okay, so with the forward, of course, it's just applying some kind of dropout. You can see that it's being applied right here. Right, the first, I think it's the dropout layer after the first fully connected layer, right? You can see here, and then of course here we apply some ReLU, and then depending on this condition here, we can apply another dropout after the second fully connected layer, and then towards the end we just apply some kind of linear, this linear function right here. Okay, and then we have our outputs. And I always test what the outputs are here. We don't have code for it, but I always test what the outputs are of the model and what the dimensions are, because that will help you to figure out whether you're going in the right direction. And then here it shows you an example of a concise implementation. Now we use the function dropout, which I really like. This is the way you learn, basically. So we implemented this dropout layer function, right, which is this one where we use for testing out what it's doing. Now we tested what it does, and then once we knew what it's doing, then we actually use it and adopt it in our in our actual neural network that we are implementing, and then we use it, right? So here with this example, it shows you how to actually do a cleaner implementation of the dropout, and you can see here that we're using the sequential module. So this one is a much cleaner implementation, and it's not really using that one that you implemented, right? So it's just using the built-in one, the NN that dropout. That's how you use it. And the same thing with the ReLU. You don't really need to implement it on your own. You just apply it right here. So all these different components of the neural network use the built-in ones preferably. And you can actually try the code on your own, but this one is just like it's just Markdown, so I won't be able to run that here. All right, so just let's use our one that we implemented, and then let's see how it does. Oh wow! So notice what happens. So I need to stop this one. The reason is because, of course, I'm printing out these things for educational purposes, but I always forget to comment them out. All right, so I think we should be good now. All right, so it's just going to do some training. You can see here we're using cost entropy loss. These are the usual functions, and it's just going to do some training on that model that we just implemented, and it's just going to try to report some of the loss here. Okay, so let's see. It's going to take a little while, I think. No, it shouldn't take too long. And yeah, play around with this one as well, right? The batch sizes, see what the effect. I think this is the right time to actually do this, because as we move forward with the program and we start to do more examples, you'll start to see all of these things kind of start to be embedded in a more high level functions and more abstractions, and then you won't really really see them. But now you see them here separately and individually. So maybe you want to try different values here and try to see what is the effect of a batch size on learning, what is the effect of the learning rate, what's the effect of the number of people. So all of this stuff this is the right time to actually experiment with that and try to see what's going on there. And if you have any questions on that, let us know. Okay, so for now we see that the training loss, okay, it's decreasing, and then we have this training accuracy and testing accuracy. Right, it looks like the model is doing well, but let's see. Yeah, so this particular model does well, and because we're using obviously the dropout, and we're using all these different things that we learn, right? The ReLU and the dropout and so forth. And so notice here oh, it's not this one, it's this one. I always keep confusing it. Just trying to understand, where we actually implemented the ReLU, where we actually applied it, and I think it's pretty similar to what you see here. That's why I showed this example here. So we have a first linear layer, we have the ReLU, we have a dropout, we have a linear, we have the ReLU, and we have a dropout. So there's like some kind of pattern. Then eventually we have the linear for the outputs. So just understand that, and you'll get an idea on how to actually compose these things. And try to add more, right? As an exercise, try to add more. Try to ignore one of these and see what's the effect of it. I think now is the right time, because like I said, everything else that you see going forward will be highly abstracted, and you won't see that again. Things will be implemented at a high level using these kind of functions here. So all of that is lost. But I think it's really good to learn this stuff right away. Okay, so numerical stability initialization. So this one is just showing you the vanishing gradient with the, let me see, what time do we have? Okay, so we have 30 more minutes. Initialization, and here is just showing you the, I think it's the sigmoid function. Let's see so sigmoid function, there, when you have, like, this is right, your typical sigmoid function is just like a thresholding effect. And then, of course, you have the gradients of that particular function, and it's just showing you here. So, what's the effect of that on we have been discussing the vanishing gradient. So if you look at the book, look at this example, it tells you right away, and it gives you a note that the vanishing gradient, when the inputs are large, right, are small and small. So here, for instance, if the let's see, if the inputs are higher, then you can see here that we want to squish them right closer to. I think we don't want them to be too small or too large, and we want to keep them constrained in some way. Okay. So you can see too large, there is some effect, or there's if it's too small, there's some where something is vanishing, and we don't want that, because we need our gradients to update our weights. And if those values are too small, your neural network is basically not going to learn anything moving forward. So that's how you would interpret it, and you can do the same thing with ReLU. Try to understand it and what the effect is as well. You can use the same code. Okay, so let's see. Let's keep moving. I really want to do the Kaggle one before we finish here, because I think that would be really cool for you to try to experiment and try it. For those of you that have not used Kaggle, that could be something exciting, I think. Right. So okay, so this one shows the exploring gradients, right? And you have like these matrix multiplications. It could be the case that you have values there that renders really like very, very large values, and that's not good for the model, as we said. and so we really need a way to control that more, right? And that's why you have those like the weight decay and so forth to actually deal with that. But this one is just going to show you here with some, like I think 100 Gaussian random matrices. Just going to show you what it does. So you can see those values here. They're either way too small, or way too large. So, and this just shows you a very simple example. But when you're training neural networks and you're adding more and more parameters, and those matrices keep growing, you have this result. You have this behavior, and so you really need a way to actually deal with that behavior, and encourage the model to kind of deal with those weights that meet that condition, like you want them to be in a specific range. We remember we said parameter values very important for model generalization, and this is a good way to test this out, to test that idea. Okay, let's check out the examples. Yeah, I'm gonna share the notebook. Again, the notebook is quite similar to what we use in the book. What I did was just select the parts which I thought were interesting and more important going forward, but there's a lot more code that I missed, right? And I intentionally do that because I think some of the things that we don't really need to cover here in detail, but these are really amazing examples because they really tell you exactly what the problem is and how you actually what's the effect of that, the sigmoid, the ReLU, and so forth. Okay, so, and then, yeah, read about this as well, the symmetry problem, right? There's actually regularization techniques, they help deal with the symmetry problem as well. So you have cases where, it doesn't matter, how the information flows. At the end of the day, you still, get the same result. And of course, when you're doing like the calculated the gradients, is the same information being propagated back, and you don't really get any learning, and you don't take advantage of that, capacity of the model. So regularization techniques help for that as well. So these things are all like interconnected. And so I think it's really good to understand them. But I don't have an example of that. What I would, however, ask you here is to try out the Xavier initialization. This one is quite an important one, I believe. And a lot of people use this in research. At least in research, I know it's being used. I don't know in other places, but this is a quite important technique. And this is about initialization, right? I think machine learning course or deep learning course, you will see this being discussed. So try to implement it and try to understand it. So implement it from scratch. You have equations online. Try to do it with PyTorch code, and that will be part of the assignment. So we have trying to put the equations on the chart here on the figure, right, of the backpropagation, and then also try to implement this and just use the same example above and try to apply it and see what the effect of it is. Okay, similar to what we did with the other initialization that we did before. Okay. All right, and if you want to take it a step further, go into the PyTorch documentation and try to see what happens when you actually plug in Xavier initialization on the model that we implemented. So this one, right? Rather than initializing, okay, so where are the weights? Where are the weights that we have initialized? That piece of code, you can actually take it and you can try to initialize it differently. And so I think that would be a good exercise for you as well, and see what the effect of it is. I mean, that's why I think the notebooks are great, because you can definitely experiment with this and try to see the effect of that. I cannot find it because it's so much code, but anyways, you get the idea. And I'll try to provide more explanation on what the assignment is and what the expected results should look like. So don't worry about it if you don't understand it right now. I'll try to provide more instructions on that. So the Kaggle summation, this is great. I think the example here, is just going to show you. It shows you how to download the data. This is the function that's being used. It's actually a function available in the D2L package. I would want to do like a little survey here. So how many of you have actually used Kaggle before? Yeah. Okay. I remember from my experience, actually my first course related to anything machine learning was a data mining course a couple of years back. And I remember the project was a Kaggle competition. It was so intimidating because I've never used Kaggle before. And actually, Kaggle was just getting started, those times. And I remember trying to, compete with in the leaderboard. I mean, it was so challenging. I mean, I think the requirements for the assignment for the project was that we needed to rank, I think, in the top 20 or something like that. So we actually, formed teams, and we needed to do, in the top 20 to actually get an A. And so we had this kind of grades. So we have top 20, you get an A. You have, maybe if you're in the top 40, you get something like a B or something like that. It was so challenging. But at the end of the day, we actually learned a lot because so we work as a group. Some people did like data preprocessing and this sort of things. And we were working, I think, on a text classification problem. And we did really well. Actually, we ranked top 20 in that competition. And it was a really good experience. I mean, Kaggle, I think it's really good, I think, to learn a lot of these different tricks. So that's when I got introduced to how to actually train models that actually work on these data, on such data sets. And those data sets are really noisy and you need to do a lot of data preprocessing. So I encourage you to try to look at Kaggle if you haven't, and work on one of the, not to compete, but just to learn, how people are actually, what kind of data preprocessing techniques people are using, right? What kind of standardization techniques they're using on data and these sort of things. And, you learn a lot about ensemble methods and these other things that are used. So it's a really good learning platform, I guess. I really enjoyed that experience with Kaggle. But after that, I haven't, honestly, to be honest, I haven't used Kaggle after that. Mostly I was just focusing on research and trying to implement models on my own. But I think, Kaggle is really a good way to get started. So as you learn things here in the program, try to apply them somewhere. And I think a good place to apply these things are in Kaggle. They even offer you, resources to participate in these competitions. So that's, I think, will be a good next step as you try to learn. All right, so this one is just going to be about Kaggle, just these functions here. They just help you extract some information. And then there's this competition here. I think I have it open somewhere. Let me try to, I think. Yeah, so I actually submitted something here. I just used the same code as in the notebook. And then you can see here that there's like a data. You can download the data set. The good thing is the code has been provided for you, and you can just directly use that code. So try to use that code and try to make a submission, and just to see how the process looks like. Okay, so that code, I won't go through all of that, but this one, really like it because the example shows you like how would you go from real world data, like actual data, not a synthetic data, a real world data, and then actually submitting something on Kaggle. So it shows you all the pre-processing steps, how do you actually prepare your data set, how to do some standardization on your data as well. How do you deal with discrete values if you want to do like a linear regression or something like that, and you want to convert your values to, I don't know, to a different kind of range. So all of that, the examples are there. And if you go to Kaggle, that's what it's about. It's about data preprocessing, and you're going to learn a lot of techniques there to do that. How to deal with missing values as well. You can use the mean of a feature to actually make up for those missing values, but there are different ways you can do this as well to deal with those meaning. And how do you learn these things? Well, I think Kaggle is a good place to actually learn it, because you will see that when people share notebooks, they're using different ways on how to deal with those missing values. Okay, so try it out, and I think that will be a good exercise for you if you haven't tried it. And then there was some, of course, I think there was a mention of we use the mean squared error loss for this simple model. I think that's being proposed here. I think it's a very simple model. I don't remember where it's being implemented. Let's see. Yeah, it's right here. It's a very simple model, like linear model that we're using on this. I'm using this mean squared loss. But you can actually, so here, if you look at the competition, and most competitions, they have like this evaluation metric, and this is why I think it's quite difficult, because they have their own metrics, right? Their own measurements that you actually need to adopt. And so in this notebook, you see that the example of this root mean squared error that's being used. If you want to learn the difference between the RMSE, the MSE, and the MAE, the mean absolute error, all of these different ones are used for different purposes. But I think the most popular one is RMSE, which really helps to determine how accurate models are. And it's really helpful, I think, with this kind of data because you really, like it says here, like you really want to understand whether whenever you have cases where you don't desire the large errors, this is the kind of measurement you're going to use. And if you look at the competition, there is like a section, I think in the evaluation section, or where they used to have it, where they actually give you this. So that's what you would use to make submissions on. Okay. At least when they're ranking your submission, that's what they're going to use. Okay. Let's see. So, and this one is great for outliers. You can read about it. I think there's one post here, and there's another post at the bottom that I provided why you would want to use this. So let's say, for a data set like this, maybe it's already really clean, but outliers are really hard. I mean, if our outliers are in your data, these are things that you really need to deal with. And if you want to find a case where you do have outliers, RMSE is a good one to use because it's very sensitive to outliers. So you'll definitely figure out that by using this sort of measurements. You can figure that out. And once you figure that out, well, the next step will be to investigate those outliers, try to see what you can do with those outliers, maybe do some extra data analysis, do some clustering or something like that, and try to understand more of your data. So this is like I say, it's a very iterative process. You go back and forth, and you try to understand more and try to optimize those models based on the things that you have learned. So that's what is implemented here, the log RMSE. And yeah, this is discussed in the book as well. Okay, and then you train, you do the K-fold cross-validation, really good example. And also books have it. This one is good to understand as well. If you're working with smaller data sets on your project, you may want to use the K-fold cross-validation. So try to look at that and try to understand how to implement it. And as it says in the book, maybe not the most optimal implementation. I know some toolkits already have this built in, but in some cases you have to implement them on your own. But yeah, just be careful when you use these ones, right? The K-fold for validation. All right, so, and I think the results are here at the bottom. You can see that the RMSE that's being outputted by this model, for the train and validation, at least you can see that the result there. And I think when you see this kind of effect, the one thing you would want to do if you're in a competition or something like that, maybe you want to submit something, right? And say, okay, you just want to test where actually you rank. But if you go into the competition itself, you will see that 0.15 or 0.17 it's really bad. Actually, some people are like 0.000 something 5. So this actually could be improved a lot. And I think this is a good way to start to test, right? So test your knowledge and experiment with different things here and change the model, make it more complex, try to understand the results, these different plots that you have here, right? And try to make more submissions. And if you see improvements, it gives you that boost. It gives you that validation that you actually are applying these things the right way. And so this is what you do. This is how you actually practice. Otherwise, this is really, really hard to practice these things and remember them and use them later on. Right, so yeah, there was some kind of overfitting here. And if you look closely, right, so we have the training and then we have the validation RMSE here, the log RMSE. You can see here that we have this one here and we have this one. Oh, for training, we have it's kind of low, and then for the validation is kind of high. So there's a hint of overfitting there, right? If that is the metric that you're interested in, you will see that there's something going on there. So maybe you probably need to pay more attention to how you're setting up this model. Maybe you want to apply some of the techniques that we discussed to test it out. And if you look at the D2L book, it gives you some suggestions on what you can actually try. So take a look at that. Let me show you what I'm talking about. So if you look at the book, it's towards the end. It gives you some exercises. Now this is not part of the assignment, but you can definitely try it, and just report and then try to share with us what you can achieve here. If you get stuck with anything and if you want to ask questions, just let us know as well. But just engage with us as you go and you learn something, and maybe you get stuck with something. So this one was actually we used the MSC laws, but you can use the log RMSE directly to make the predictions. So try to use that as proposed here. And I look at the conversations here at these PyTorch. I look at the conversations were really nice. Take a look at the conversation as well. There's some interesting questions going on there, and this is how you learn. And try to maybe tune the hyperparameters. Try to see if you can get that those results. If you can get better results, that would be great. Use the weight decay, dropout, and so forth. All these different things that we learned. This is the time to start to implement and apply those things. This stuff is you can learn all the theory, right? You learn a little bit about all the different techniques, but this stuff is easy to forget. Believe me, by experience, I could tell you, it's really important that you apply them. Either to your research now or use Kaggle, use competitions like this to practice, keep on practicing. Otherwise, it's really, really hard to actually stick with this information going forward. Okay, I guess we can have a discussion, and we have, let's see, I think that's the end of it. And I did make a submission, like I said. I think there's a function that actually allows you to do set up a submission. But look at the code, go through it, try to understand it, and see how you can actually come up with the submission. The submission is quite simple, actually. Let's see here. It's just this, right? So in most competitions, you only need to provide the ID of the data set. I think this one is a test data set, and then the sales price, that's the output of the model predicted. So take a look at that, do some more analysis on that, and try to understand it and make some more submissions. And I'll be interested to see your results that you get and have a discussion around it. Okay, so let's go to chat. Any questions? Maybe we can have a discussion now. I think we have, let's see how much time, 10 minutes. Any questions? Please let me know. Yeah, someone didn't have the courage to submit. I think what could really encourage others, I guess, is to form teams. So you can actually form a team. We could form a team if you all like that. We could actually form a team and we can experiment with it as we go forward. I think it could be a really good way to practice. Create a team for the Slack group, and then we can actually try to submit something. But yeah, I really encourage you to practice. Otherwise, this stuff is gonna go away soon if you don't practice it. Okay. All right. So just your feedback here. If you don't have any questions, was it useful? How's everything going? The slides, are they useful? Hopefully you learned something here. If there was anything I made a mistake on, please ask me. I'll try to maybe give you some more insights or try to share some more resources with you or something like that. But hopefully you got the idea of the chapter. I think it's a really great chapter. It really covers the most important stuff, I think, when training neural networks. All this stuff like weight decay, dropout, how to apply them in neural networks. This stuff is really about it's very iterative process. You really need to. There's no like magic formula in how to combine these different things and techniques. It's all about experimentation, and I like that the book actually offers you the necessary code, the necessary functions to try these things and try to understand them on your own and get some more intuition. Obviously, they won't go through all the details and try to make you understand everything, to really fine-grain detail, but I think they give you the building blocks to achieve it and help you with your learning. Okay. All right. So any questions anyone wants to ask, any comments, any feedback, I would appreciate it. Feel free to do so. Yeah, I mean, I think for me, it's most of these things are revisiting. Like I'm revisiting all of these things, but I could definitely see really unique things with the way the book provides code. what I used to do before. I try to implement things on my own. So I would go to like a Wikipedia and try to implement on my own. Because there weren't, or at least when I got started with studying, there weren't too many like communities where I could go and ask a question. I would mostly use the Stack Overflow, but Stack Overflow could sometimes not be so reliable for answers. But I would try to implement things from Wikipedia directly. But having this sort of like resources like these books where they implement things for you, and all they tell you is try to understand it a bit more by reading other things online and giving you the kind of the guidance for understanding these things, and they give you code examples which you can easily extend. This is really, really great stuff. And that's why when I saw the book, I wanted to do a study group around it, because I believe this is the way you learn. Like, you really need to experiment with it. You can learn the theory, but if you don't know how to apply it, I think it's going to go away. And it's a quite exciting thing to learn these things and apply them in your problems wherever you are. Yeah, it's intense. Even for me, like I said, it's more like recap for me, but it's intense putting the slides together and trying to decipher what is the most important one. There's a lot of noise, to be honest, like a lot of examples that I don't think make sense to discuss now, at least. But I think as a lecturer, I'm kind of using this as a practice as well. And that's why I'm enjoying this, because it's quite intense for me to put together slides and try to show you the things that matter, and then going through the code watcher as well. It's kind of challenging as well. But I think one of the things that I will try to do later on is to actually come up with a course for this, and this will be one of the resources I'll be heavily relying on. But there are other resources that I use as well before to learn this stuff, and I'll definitely be incorporating a lot of ways to get more intuitions and try to expand on the examples. So definitely there will be a course, I guess, for people that want to go more advanced, right? So how would you actually, for instance, apply this in for research? How would you actually set up some experimentation environment and this sort of things? So I think that will be a next good step that I'm kind of considering as well, but I haven't really finalized that. I'm thinking about it. I think we really have spent a lot of effort on this one and learning it, but I think as a next step, we definitely want to take it to the next level. So these are things to keep in mind. All right, I guess that would be it. So no questions so far. So I'll post the recording for the other chapter. Please check it out. That recording will be super important going forward. That one will start to talk about how to more efficiently use the library, right? And different tricks on how you would set up your neural networks and so forth, right? The conventions that are being used and all of these different things. So please check that out when I post it. I'll post it in the Slack channel as well. That will be a very important one. And then next week we have Salim. I think he will do consecutively two weeks, so 2 sessions on CNNs. So quite excited for that. And we'll talk to you again in the next sessions, I guess. So thank you again. Have a good rest of the weekend, I guess, and we'll speak to you soon. Bye.